So we are doing problem number 12. The half-life of the radioactive potassium is 1.3 billion years. If 10 grams is present now, how much will be present in 100? All right, so this is a half-life. Anytime there's a half-life, you use the radioactive decay formula, which is this right here. It's, sorry for that not being very good, but this is the original amount. This is the final amount. And K is some constant that we need to find, and T is in years. Alright, so we're going to find K by plugging in. They basically gave us a point. They're telling us that 10 grams are present now. Well, I'm sorry, that's not the point. They're saying the half-life is 1.3 billion. That's our point. They're saying that when A sub 0 equals 2 times, when 1/2 of A sub 0 equals A, they're basically telling us that when we're at half of our original amount, so we have half of our original amount, they're telling us that the time is 1.3 billion years. So K to the 1.3 billion years, which is 1, 3, and a bunch of zeros after it. I'll clean that up in a second. Okay, so these A sub zeros are going to cancel out, and we're going to have 1/2 equals E to the 1300, let's see, billion, 000,000. Is that billion?
Mm-hmm.
Yep. Times K. That's our equation, and we can solve for K by taking the natural log of both sides. When I take the natural log of this, that goes away, and I just get the natural log of 1/2 equals 1.3 billion K. 1.3, let's see, billion would be what, 9 times 10 to the 9th. Now I'm changing it to scientific notation. Sorry, I'm teaching you a little bit of everything in here. And now we solve for K by dividing both sides.
Wait. Do you have to do like the 1.3 times 10 to the 9th? Yeah, because
You should. Or if you don't do 1.3 times 10 to the 9th,
Which is
T is
1.3.
going to be in 1.3 times. If you just did 1.3,
Yeah.
then T is in billions of years.
That's why it's like negative 23.
That's fine. You can do it like
Okay.
that.
Oh, really? Okay.
But if you wanted to keep T in just in years, then put 1.3 times 10 to the 9th. That's what I would do. So there's your factor of K. Now let's use that, and 10 grams is present now. That means A sub 0 is 10.
Mm-hmm.
So what's the new amount? If 10 grams is present now, what's the new amount in 100 years? So we're plugging in 100 for T. See if 100, you couldn't, if you put just 1.3 here and you plug in 100, you're going to get the wrong answer.
Oh.
Because you're putting 100 years, and your T would have been in billions of years.
Oh.
So you'd have to convert 100 to
2
billions,
billion.
and that's more confusing.
Okay.
So that's why I would just do it like that, and then our answer is going to be 100 times. Let's call this thing C. Whoops. Let's call that thing C. Whatever C is times 100 is your answer. So you can even use your calculator. You could punch that in, you could store it, and then you could type this right into your calculator. And when you do that, you will get